Hey everyone, welcome to The Explainer. Today we're diving deep into the absolute bedrock of, well, everything digital. We're going to get to the bottom of the simple yet totally brilliant components that make every single device you own work. I'm talking about logic gates.
I mean, just think about your phone for a second, or your laptop, your smart TV, anything really. They do these incredibly complex things in like the blink of an eye. But how? How does that even work? Well, it all comes down to billions, and I mean billions, of tiny microscopic switches, all making the simplest decision you can imagine, on or off.
All right, let's really get into this. If you want to understand how a computer thinks, you've got to start with its most basic language. And no, it's not code, it's not software, it's just electricity. And that electricity, it can only ever be in one of two states.
And that, right there, is the binary system. Every single piece of data, I'm talking everything, from a single letter in a text message to a full-blown 4K movie, gets broken down into a long sequence of ones and zeros. A 1 just means there's an electrical charge, it's on. And a 0 means there isn't one, it's off. That's it. It's the simplest alphabet imaginable.
So, what's actually doing all this switching? Well, the hero of our story today is the transistor. This thing is a microscopic device, and I'm not kidding, you can fit billions of them on the tip of your finger. It's the physical thing that acts as that 1 or that 0. It is the switch, the little guy that can be either on or off, letting us control the flow of that electricity.
Okay, now don't get bogged down in the super technical details here. Let's just focus on the core idea, which is actually really simple. See that control wire in the middle? Just picture it like a regular light switch on your wall. When a tiny bit of electricity hits that wire, bam, it flips the switch on, that opens up a path, and a much bigger electrical current can flow right through. But if there's no signal on that control wire, the path stays closed. Simple as that. It's a perfect little switch controlled by electricity.
So, having billions of these on-off switches is great and all, but right now it's just a giant collection of switches. The real magic, the good stuff, starts when we arrange these transistors together to actually make decisions. So how in the world do we get from a simple little switch to something that can actually perform, well, logic?
That's where the logic gate comes in. You can think of a logic gate as a tiny decision-making machine. It's built from these transistors, and what it does is it takes one or more inputs, those same ones and zeros, and then, based on a very specific rule, it spits out a single output. It's really the first step up the ladder from just on-off to actual thinking. And that name, gate, is actually a perfect metaphor. Think about it. Just like a real gate in a fence controls who gets to pass through, a logic gate does the exact same thing for information. It controls the flow of those electrical signals, our ones and zeros. So, what are these all-important rules? Well, what's really amazing is that pretty much all of digital logic, everything your computer does, can be built from just 3 basic operations. So, let's meet the big 3: the AND gate, the OR gate, and the NOT gate.
First up, we've got the AND gate. The easiest way to think about this one is like a super strict security checkpoint. To get through the door, that's our 1 or on output, you need to have your key card and your security badge. If you only have one of them or you have neither, nope, the door stays shut. Your output is a 0.
And this little chart here, this is called a truth table. It just shows every single possible outcome. So let's take a look. If both inputs are 0 or off, the output is 0. Makes sense. Now look at the next 2 rows. If just one is on, the output is still 0. See? The only time we get that 1 output is way down at the bottom, where input A and input B are both 1. That's the whole rule right there.
All right, next up is the OR gate, and this one is way more laid back. A great analogy is a fire alarm. The alarm is going to go off, that's our 1 output, if it detects smoke, or heat, or carbon monoxide. It doesn't need all 3, right? Any single one of those is enough to set it off.
And yeah, the truth table proves it. Look how different this is from the AND gate. The only possible way to get a 0 for an output is if both inputs are 0. If input A is on or input B is on or both are on, you get a 1. As long as at least one condition is met, that gate is wide open.
And finally, we have the simplest gate of them all, but you could argue it's the most important one, the NOT gate. People also call it an inverter. And it does, well, exactly what you think it does. It just takes a single input and flips it to its opposite.
I mean, look at its truth table. It couldn't be simpler. If you put in a 0, you get out a 1. If you put in a 1, you get out a 0. That's the whole show.
But don't let that simplicity fool you. This ability to just flip a signal is absolutely 100% crucial for building anything more complicated.
So here's the big takeaway. These three simple gates, and, or, and not, they're basically the Lego bricks of the entire digital world. By snapping them together in all sorts of clever ways, we can build circuits that do literally any logical task you can think of. I'm talking everything from simple math, like adding two numbers, all the way up to running a full-blown operating system.
Okay, let's look at a real, concrete example to make this stick. In this security system diagram, you see that access is only granted if the key code is valid and the badge is valid. Boom, that's a perfect AND gate in action. And then look below that, the light comes on if it's dark outside or the room is occupied. That's our OR gate. It's a really simple, clear, real-world example of how these basic gates work together.
All right, so let's zoom out for a second and just appreciate the scale here. These incredibly simple rules, performed by billions of gates, millions of times a second, that's what gives a computer its power. It's really a beautiful thing. All of this mind-boggling complexity just bubbling up from a few simple rules.
And of course, this didn't just happen overnight. This whole idea started way back in the 1800s with a guy named George Boole and his abstract math. Then, this other genius, Claude Shannon, came along and made the brilliant connection between that math and electrical circuits. Then came the transistor in 1947, which gave us the actual physical switch. And finally, in the 60s and 70s, integrated circuits let us cram millions and millions of these things onto one tiny little chip.
And this, right here, is why all this matters. The purpose of these logic gates, it's everything. They are the absolute foundation for everything a computer does. You want to add two numbers in the CPU? That's just logic gates. You want to save a file to memory? Logic gates again. Controlling an elevator, displaying a number on a screen, a safety alarm going off? At the end of the day, all of those things are just incredibly fast, incredibly complex arrangements of these simple, little building blocks.
So really, the next time you pick up your phone or sit down your computer, just take a second to remember what's happening under the hood. Billions of tiny little gates opening and closing at insane speeds, processing information based on the simplest logical rules you can imagine. And it kind of makes you wonder, right? If all the mind-blowing complexity of our modern world is built on just three simple ideas, and, or, and not, what are we going to build with them tomorrow?